Hi! In this exercise we're concerned with the conduction electrons in silver. Silver has the atomic number 47 and it has a density which you can see here, and also an electronic configuration, and I've circled the 1 here since it means that it has 1 conduction electron that contributes per atom to the conduction band, and it has an atomic mass, as you can see here. And we would like to calculate first the conduction electron density, N, and then we would like to determine the Fermi energy using the free electron model. So, in order to do that, we'll basically start by deriving N here, which is equal to the number of conduction electrons divided by the volume. And you can simply just change the volume for mass divided by density. And in the end you get, if you replace the number of conduction electrons per atom, which is 1, using this, and then instead of using the total mass, we'll use the mass per atom, which is the atomic mass, and putting that in, we get the result here. So, in terms of the Fermi energy, we'll use the fact that electrons in a box would basically correspond to standing waves in a free model. And we basically can use the argument that electrons are waves, and they have a certain wavelength as well. And the wavelength divided by 2 times a certain number, integer, would equal the length of the box. So using that argument and the wave vector, which is always equal to 2 pi over lambda, then exchanging lambda for this expression, you get that the wave vector for the electrons is basically an integer times pi over l. Well, why do we want to use this? Well, the Fermi energy is basically the energy that bounds the occupied states from the non-occupied states. And in terms of a k-space, the volume of one orbital is basically the number of kn that you can fit, right? The volume in k-space that you fit 1 kn in, and that must be pi over l times to the power of the dimension, right? So we have 3 dimensions. It should be pi over l to the power of 3. And this boundary here is basically the maximum kf, which is the k Fermi, and the complete volume of this should be the number of states you have would be 2 in each box, corresponding to spin up and spin down, and then times the total volume divided by the volume for one of these boxes. So basically we have the number of electronic states is divided by the number of spins per orbital times the total volume of this complete sphere. And since the sphere contains 8 of these quadrants, we take 8 times the volume of this orbital, and then basically from this we would get this relation. And using this relation, we can find out basically what the k Fermi energy is. The k Fermi wave vector is, which is n, well, it's related like this, if you put in the values here. And from this we can calculate the energy, and in a free electron model, the energy, the momentum is just h bar divided times k. And using this fact and replacing this, we get the energies. And then just putting in the Fermi energy instead, replacing the arbitrary k with the Fermi k, gives us the complete solution for the Fermi energy. And you can write it down in joules. And just by multiplying by the electrical charge, you get it also in terms of electron volts.
Hi,
So this exercise is about density of states in silver. And we're going to use the fact that we know the Fermi energy and we know the conduction electron density. And the basic question is, what is the density of states per volume at the Fermi energy? And well, basically the density of states can be calculated by taking the derivative with respect to, of energy of the number of electronic states in the system. And without going here yet, we'll use the fact that first the number of electronic states can be derived by multiplying the number of spins per orbital times the total volume bounded by a certain energy in k-space divided by the volume of a certain orbital. That will give us the total number of electronic states in the system. And by putting in the volume of a sphere here and the pi over L cubed and 2 here, we'll get this expression. And the wave vector or crystal momentum for the electron can be calculated in the free electron model as the square root of 2me divided by h bar. And using 1 and 2 here, we can insert that in this and here. And just by doing the calculation, we get the expected result of the electronic states. And also you have to do the derivative. So the derivative of, if you don't do the derivative, you get e to the 3/2 divided by 3p2, p squared, pi squared. And if you do the derivative, you get the square root of e divided by 2 pi squared. And basically just putting in the Fermi energy in this result here, we'll get this result in SI units. And since we want to get this in per electron volts per atom as well, well, this was the main question, to get it both in joules and also in electron volts per atom. And by multiplying with the electronic charge divided by the known conduction electron density, we'll get the value in per electron volt per atom. In this problem, we're concerned with the reciprocal lattice of IPCO. IPCO contains yttrium, barium, copper, and oxide, and it is orthorhombic. Orthorhombic basically means that all sides do not need to be equal, but the angles are right angled in the corners of the unit cell. And basically, the two problems we want to do is basically determine the reciprocal lattice vector for IPCO using these facts here, and also calculate the length of the reciprocal lattice vector with the Miller indices 1, 1, 0 in IPCO. And in order to do that, we'll basically just use the definition of what the reciprocal lattice vector is. It is 2 pi times the cross product between the other two lattice vectors. That is, if you have 1 there, you have 2 and 3. If you have 2 there, you take 3 and 1. And if you have 3 there, you take 1 and 2. And then you divide by the total volume of the cell. And you can see that putting in the values, you know that they're right angled, and you can use the fact that the a-axis is along x-axis. The b-axis corresponding to b here is the y-axis, and c is the z-axis. And putting in the values for the volume, which is just a times b times c, and putting in the values here and doing the cross product, you get the result 2 pi over a times x hat. And just by symmetry, since I mean the only thing that is the difference between these three axes is the length of the cell in that direction. So you can directly put out the other two, even though you could have done the calculations yourself. So it's a good exercise to try that. And the second problem was that we want to calculate the length of the reciprocal lattice vector that has the Miller indices 1, 1, 0. And basically, the definition of this is just that you take this number times the first reciprocal lattice vector, plus this number times the second reciprocal lattice, and this number times the third reciprocal lattice vector. And so you have 1 here, and then the 0 cancels the B3. And the length of this vector would be the length of that. So putting in the values of what we just calculated yields 2 pi times this expression, and putting in the values for A and B resolves in 2.308 angstroms to the power of -1. So in this problem we are going to calculate the density of states using the free electron model. And we're going to do it in 2 dimensions. And in 2 dimensions basically we'll calculate it as the derivative with respect to E of the number of electronic states in the system still, right? Even though it's a 2-dimensional system, but you divide by the area here instead. And you use 2 facts. The first one is that the number of electronic states, again, is the number of spins per orbital times the ratio between the total area in the K space of allowed electronic states divided by the area of one orbital in that sense. And you can use this picture here where the total number of states that are allowed is this piece here, basically the positive values of kx and ky here, and the volume or the area of one of these orbitals is denoted by a orbital here. And you just put in the value. You take pi times k squared divided by 4, because it's 4 quadrants. And then you divide by the area, pi over L squared. And you get this result here. And you can use the free electron model to calculate what this k squared is. It's basically 2m epsilon divided by h squared, h bar squared. And putting this in, it seems like we get a constant value for the electronic density. The density of states, which is m over pi h squared, h bar squared. Hi. So in this problem, we're concerned with the brilliance zone of silver, and we want to calculate the distance from the gamma point to the high symmetry points x, k, and l, which are all lying on the brilliance zone border. And in order to do that, we need to understand that silver is phase center qubit, meaning that it has the lattice vectors are corresponding to these 3. And if you do the calculations and calculate the reciprocal lattice vectors, you will get that B1, B2, and B3 corresponds to a BCC. And so actually, if you have a FCC in real space, you will always have a BCC in reciprocal space, and vice versa. If you have a BCC in real space, you will get an FCC in reciprocal space. And as you can see here, the distance between the lattice points in a BCC that corresponds to the reciprocal space of a FCC will have the spacing of 4 pi over A. And we will use that next when we're trying to map out in the BCC lattice where these high symmetry points are. And looking here, you have one lattice point here and one lattice point here in a BCC. So this would be 1/8 of 1/8 of one of these cubes here. So the corner here and here corresponds to the corner there and one of the corners here. So we want to calculate the distance. So the distance from gamma to x, and you can simply see that in this, when we have drawn it this way, you can simply see that this results in 2 pi over a, and put out is 1.536 angstroms. And for the distance between gamma and L, you can see that it is half the way from one lattice point to the other. And this distance here must be 2 pi over a times the square root of 3, right? That's the long diagonal in a cube. And half that distance gives you square root of 3 times p divided by a, which basically results in 1.333 angstrom to the minus 1. So to end with, we have to do some geometry here, and we want to calculate the distance from the gamma point to the k point. And what you can do is basically map out the triangle that goes from the gamma up to this lattice point here and down to this point here, which corresponds to this triangle here. And according to known laws of mathematics, is that the ratio, this distance here divided by that distance must be equal to the long diagonal here divided by this one, meaning that gamma k divided by gamma L equals square root of 3, which is the long diagonal, and divided by square root of 2, which is the short diagonal. And it doesn't matter which sides these are, the ratio would always will cancel out the a. So this means that you get gamma k, the distance gamma k, equals to this relations here times this one, which is equal to that one, times this relation here. And this gives you 3 pi divided by square root of 2a. And put it out, it's 1.629 angstroms to the minus 1.